All right, we are ready at the start time, 2 o'clock Eastern Standard Time, so we will begin. First off, good afternoon. I am Jason Thomas, Project Engineer at America Makes, and your host for today's America Makes TRX webinar series. Little background on the TRX webinar series before I introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange webinar series, was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer or Q&A session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we will ask it during the Q&A session. We will do our best to get all the questions answered. Today's webinar is on ICME methods for fatigue performance prediction of metal AM components. Without further ado, it is my pleasure to introduce our presenters, Mike Oya, Animesh Day, and Bob Tryon from Vextec. Mike is a sales and project manager with Vextec. Mr. Oya has been affiliated with Vextec since 2005 after graduating from the University of Utah. During his time at Vextec, he has held various titles, and most recently the dual role of sales and project manager. He also spent 3 years in the manufacturing sector as a materials and process technology engineer for a global supplier of critical military and commercial aerospace components. He has authored or co-authored 7 engineering papers and is a U.S. patent holder. Animesh is the Chief Product Development Officer with Vextec. Dr. Day is one of the co-founders of Vextec and has over 20 years of experience in probabilistic structural analysis. He leads the VPS-MICRO software development team at Vextec. He has been a lead researcher in several programs for the Air Force, Navy, Army, DARPA, and NASA. Animesh received his PhD from Vanderbilt University. He has published over 30 papers in engineering journals, and additionally, he holds 5 patents. Bob is the Chief Technology Officer with Vextec. Dr. Tryon has over 30 years of experience in engineering fatigue analysis and computational material science. He is the inventor of Vextec's patented probabilistic microstructural simulation approach, known as VPS-MICRO. He has led research programs for the Air Force, Navy, Army, DARPA, and NASA. Bob received his PhD from Vanderbilt University and his undergraduate and master engineering degrees from Rose-Hulman Institute of Technology. He has published over 30 papers in engineering journals, and additionally, he holds 7 patents. Mike, Animesh, and Bob, I will now turn it over to you and your team.
Thanks very much, Jason. This is Mike Oya speaking. We're excited to talk today about the role that ICME methods can play in performance prediction of additively manufactured parts. And for those of you not familiar with the term, ICME stands for Integrated Computational Materials Engineering. Now, a lot of attention is paid in ICME, and rightly so, to the process modeling aspect of AM. That is, to help determine what speeds and feeds are appropriate in a given application to optimize the build process. But ICME can also be used further downstream to help understand the performance capabilities of AM components. This is especially important when considering the impacts to verification and certification. The goal of this webinar is to introduce you to some of these methods and to get you thinking about how you can start using them in your own product lifecycle management activities. I'll first hand the presentation over to Animesh, who will give you a brief introduction of our company, as well as describe what we mean when we talk about incorporating ICME into an AM certification process. We'll also discuss our ongoing AM work with the U.S. Air Force. Then you'll hear from Bob as he introduces you to our ICME-based software, which is called VPS-MICRO. I'll return at the end of the presentation to go through a live demonstration of our software with a real-world example of an additively manufactured titanium alloy. And then we can wrap up with some questions. So, Animesh, the floor is yours.
Mike, as an introduction, Vextec is a software as a services company out of Nashville, Tennessee. as Mike said, our software VPS-MICRO. It is a computational tool to predict the risk of failure from metal fatigue. And the value proposition for using VPS-MICRO is to supplement physical testing for accelerated part qualification with increased confidence. Over the past 2 decades, we have successfully helped clients all over the world across different industries, ranging from aerospace, medical devices, heavy machinery, where the risk and potential consequence of metal fatigue failure can be high. This technology of ours has matured and been validated through several Department of Defense programs, and Vextec and VPS-MICRO is backed by 7 US patents. Next slide, please. So taking a closer look at how our clients benefited, I mentioned earlier that the value proposition is to supplement physical testing. Specifically, VPS-MICRO has been successfully used in qualification of new materials. Often people refer to it as second sourcing as well. In a very similar vein, recently our clients have also used the tool to certify AM materials. Again, it is very analogous to second sourcing, where we're attempting to replace perhaps the original cast material with equivalent AM materials. And finally, because our software tool is probabilistic and uncertainty based, through simulation, it has also been used to ID field failure issues related to fatigue not covered during the initial testing phase. If we go on to the next slide, please. I think we in general all recognize that, AM certification and development process is iterative and can be costly and slow. On the top right, I'm sharing a graphic from DARPA, which in general illustrates this point and further highlights that the cost of this iteration increases later in the design cycles, issues and flaws are identified. So the challenge is universal to accelerate the certification process by reducing time and money required. This is more of a challenge for new manufacturing methods such as AM as compared to conventional methods such as forging or perhaps casting, where there is significant wealth of past experience and data. And thus, we're proposing that appropriately, if we can supplement this build, test, analyze, repeat cycle with computational tools and software, we should be able to accelerate the development and certification process. So if we go to the next slide, please. So what do we mean by when we say ICME-based certification? We are not changing the required elements of a certification process. Instead, the focus is to use simulation and appropriate software and computational tools to gain confidence in the build process. And then once sufficiently one understands the initial uncertainties and their sensitivities, especially in the context of AM, the speeds, the feeds, how it then impacts the resultant material microstructure variability. And then from the resultant microstructure, how does that impact the fatigue performance? If this cycle of build, sense during build, simulate, and then repeat till we gain adequate confidence, we should be able to accelerate the certification process. Next slide, please. I just want to highlight a couple of issues with respect to metal additive manufacturing, where computational tools such as VPS-MICRO has been effective in predicting part performance. And again, this is relating the microstructure to the performance. One such important issue, I think you all will recognize, is as-built surface morphology. Especially critical when considering that AM is quite attractive for building parts with complicated geometries with lots of internal unfinished surfaces. I think what you're seeing here is an image of AM Ti64, and you can readily identify that, you know, the surface is quite rough. Conventional way of accounting such features is perhaps to take, you know, a smeared approach, maybe look at the RA, SA kind of features, characterize the surface profile, and then calibrate it to fatigue parameters. We feel and recommend that a parametric approach might be more effective in understanding which features are most critical to fatigue performance. I mean, even in this picture, you're seeing that these rough surface can be, is made up of, you know, bumps, crevices, ligaments, and such. And if we understand the sensitivity of these features to, let's say, what the stress profile and the performances, we should be able to understand which features are most critical. Next slide, please. So here we're showing you a simplified sort of stylized model of a rough surface, similar to what you saw in the previous slide. So on the left-hand side, you see sort of the geometry. And this geometry is made up of spherical bumps, you know, and then there are pits or holes into the surface. And in between, I guess, neighboring pits or neighboring bumps and pits, there's that transition which we were characterizing it as ligaments. And on the right-hand side, you kind of see the corresponding stress model. So what becomes readily apparent in this kind of a modeling technique is those raised bumps, they are really not, you know, important as far as carrying the stress. They have the lowest stress. However, those holes, the ligaments and such, they are the ones where there is stress concentration. And if we can characterize the uncertainty in these stress concentration profiles, both in terms of the magnitude and the die out, and be able to incorporate this in a computational model, we should be able to computationally and distinctly predict, you know, how the rough surface would impact fatigue performance. And later you'll see Mike will show you an example of how this can be incorporated into the model. I think we have known that in AM process, there is a dependence or variation on fatigue performance based on build orientation. Again, here's an example I'm showing of, you know, EB Ti64, and on the left, and there are two build orientations. So on the left-hand side, you see the build direction is vertical, and the loading direction is orthogonal to the build direction. And on the right-hand side, the build direction and the loading direction are parallel and collinear. And based on experimental data, it is clear, it has been observed, you know, that when the build direction and the loading direction are perpendicular, this material exhibited higher tensile strength and a smoother fracture surface. as opposed to the other case where they were collinear or parallel. It had a slightly lower tensile strength. There were build defects that became active, and it had a rough fatigue fracture surface. Again, empirically and through observation, we understand that. So, however, the challenge is how do we kind of put these kinds of observations into a mechanistic model where for the same material based on orientation, loading direction, one can change certain properties mechanistically and be able to predict the performance. Again, later in the presentation, you'll see such an example where we are able to characterize these mechanistic differences into our modeling technique and predict the fatigue performance. Next slide, please. So all of these issues that I just mentioned, these are active areas of research, and Vextec is involved with the U.S. Air Force to investigate and formulate solutions based on mature software tools to see how these tools can be linked together in a computational sense to accelerate and scale up metal additive manufacturing. One such program is with the Air Force Lifecycle Management Office, the Rapid Sustainment Office. And again, Vextec is partnered with UTC and UDRI to kind of create a rapid qualification framework for metal additive manufacturing. Again, the goal here is to demonstrate where computational tools, both from in situ sensing to kind of looking at post-build microstructure and then eventually linking it to the fatigue performance, how can tools such as ours and others be used to accelerate and scale fatigue performance? Another program with the AFRL is to look at specifically how, as I showed you earlier, surface morphology can be put into the model in a mechanistic or computational sense and characterize its sensitivity and resultant performance on fatigue properties. So with that bit of preamble of what we mean by ICME-based certification and a few issues, I'll turn it over to Bob now, and he will give you a more in-depth overview of the VPS-MICRO modeling paradigm and underlying mechanisms. So Bob?
Okay, thank you, Manimesh. As Manimesh said, I'll give a kind of an overview of the software product VPS-MICRO. And just as FEA models the geometry and strength and loads of a macrostructure, VPS-MICRO models the geometry, strength, and loads of a microstructure. And if you were to view a metallic product under the microscope, you would see this seemingly random arrangement of grains, grain boundaries, pores, inclusions, and such. And it is this microstructure, this very small structure, that really governs fatigue cracking. And it's the random nature of this microstructure that drives the large uncertainty that we see in fatigue lifetimes, which makes fatigue testing so expensive and time-consuming, because you have to test a lot of specimens for a long time to understand what the true minimum fatigue properties are. Now, how does all this go about affecting product certification? Well, kind of the risk of product failure is represented by the graphic up here on the upper right. And it's a typical interference chart where the blue line represents the variation in the load on the product, and the red line represents the strength of the product, and that yellow region represents the probability of failure, the interference of strength with load. Now, for many years, or many years ago, actually, we made interference charts by testing many products. But now that blue line can actually be estimated using FTA and Six Sigma methods, and that's been true for a couple of decades now. The issue is that traditionally the red line is determined with large and expensive fatigue test programs. And this is where VPS-MICRO comes in. It's a computational software to estimate the red line in much the same way that Six Sigma and FEA can estimate the blue line and thus cut the overall time and cost of the to certify structural components. Next. So VPS-MICRO takes the traditional FEA-based structural analysis and superimposes at the elemental level the microstructure of the material to predict the statistical distribution of fatigue cycles to failure. And to do this, the software simulates the damage accumulation process, starting at the initial crystal plasticity to nucleation of a crack, to small flaw fracture mechanics, to linear elastic fracture mechanics. So it follows that process through its various stages. And not only can this be used to predict the risk of failure of a structural feature, but it can also be used to, in the design sense, to know what microstructure is allowable at each location of a part. And this is especially important in AM metal products where the microstructure can vary throughout the part depending upon where that location is on the build plate, how thick that particular location is, and during the processing, the heat transfer that takes place in the creation of that microstructure. Next slide. Now, in recognizing the product failure as a process and not an event, and that there's much uncertainty in each stage of that process, to simulate the risk of failure, we need to propagate the uncertainty from process model to process model. By process model, I mean the actual failure process modeling, which can start with the uncertainty in the FEA model, including uncertainties in geometries and loading. And this is used along with the uncertainty in material microstructure, and also the uncertainty in the models themselves, modeling uncertainty, but propagating that uncertainty from all of its sources to the uncertainty in the final result, which is cycles to failure. And by considering the failure process, we're able to use all of the available knowledge. And by using physics-based computational models, we're able to explicitly propagate uncertainty from various failure processes to the others. And then when new models or new data become available, the process modeling can be updated such that you can bring all of that new knowledge into it. And this is kind of what's going to be called the digital twin. And these are kind of the elements of the digital twin. So if you think about it, we're kind of building part of the digital twin of the AM product. And Vextec software has been used for, as I said, for a number of years, and it's to model fatigue at the microstructural level. And it's just been used for forgings and weldments and castings. And what we have found is that castings can have a similar attribute to AM products. And this is just an example of a cast iron connecting rod. And although connecting rods have been around for a century, and of course cast iron has been around for millennia, our customers have still been able to use VPS-MICRO to optimize the design of something as traditional as a cast iron connecting rod, because the model allows you to recognize that the material properties vary dependent upon the location of that casting. And you don't have to assume minimal material properties throughout the casting. And thus you can optimize and make lighter that connecting rod, which makes it easier to certify that rod for use. And go to the next slide. And in a very we've also noticed a lot of similarities with actual forgings, because we've kind of found that the difference between a conventional process metal and AM metal can be captured through the quote-unquote microstructural definition. And here's a case where we've got a beta annealed forged Ti-6-4 from our material library, and it has many attributes similar to an electron beam melted AM Ti-6-4. The difference is that there can be differences in grain sizes. A lot of times the grain size is an order of magnitude smaller because of the quick cooling rates of the EBM Ti-6-4, but also the effect of defects. And there can be a trapped gas, porosity, unmelt particle inclusions. And if you can identify and capture those and put those into your model and use as a baseline the forged Ti-6-4, we've been able to model the AM Ti-6-4. And this is an example that I'm going to hand back to Mike, and he's going to actually show this, how we can go about doing this. Mike?
Thanks, Bob. So before I show you the software, I'll set up this kind of example problem that we're going to look at. Here I'm showing examples of two different fatigue specimens. The upper image are specimens machined from a forged beta annealed Ti-6-4, and the lower image shows Ti-6-4 specimens produced via electron beam melting. The image here shows unmachined specimens, but we'll be simulating specimens that have been surface machined so that the roughness is reduced. And I'm going to use VPS-MICRO to simulate the generation of a standard stress life curve, an SN curve, through fatigue testing. You can see the size and the dimensions of the fatigue specimen in the drawing at the bottom, and the calculated surface area of the specimen's gauge section of 0.09 square inches. And we'll first be simulating the forged specimens, performing constant amplitude fatigue testing at 6 different load levels, so a loading ratio of minimum to max of R equals 0.1. We'll look at simulating 100 specimens for each load level, and if you think about how much time and cost that would take if you were to physically perform these 600 total tests, that's quite significant. We'll then move on to showing what simulations of EBM Ti-6-4 would be and how they would differ from the forged condition. So with that introduction, I'm going to move into the live software and give a quick overview. In the upper left-hand corner of the VPS-MICRO software interface is our Material Explorer, where you see the library of materials that are in the software. Vextec has a large baseline library of publicly available materials, and this is a portion of that library. We're going to focus on the forged beta Ti-6-4 that is selected here for the moment. On the right-hand side of the interface, you can see all of the modeling parameters for this material. They're organized into 3 main categories: bulk properties, phases, and long crack info. VPS-MICRO's models are truly mechanistic models, as we've said before, and they treat fatigue as a process instead of an event. The bulk properties and the phases tabs in the software develop the models for the nucleation and the small crack stages in fatigue. And the long crack info develops the modeling for the long crack stage. And all of the dozen or so material property inputs that you see here are accumulated through standard ASTM type tests like metallography, tensile testing, fatigue crack growth testing. And the material parameters you see here are for our forged beta Ti-6-4 specimen. Below the Material Explorer, you'll see the Design Explorer. And this is where inputs such as global geometry are found. As you recall from our example, we'll be modeling constant stress fatigue specimens with our gauge surface area of 0.09 square inches. If we wanted to model larger specimens, we could use the area factor here and put in a value greater than 1. If we wanted to model more complex geometries like notches, bolt holes, or the like, we could use outputs from a commercial FEA package like Abacus and ANSYS. Vextec has developer partnerships with these organizations. The next step in the Design Explorer is the Loading Definitions page, where we'll be defining the 6 constant amplitude load levels in our example as maximum and minimum stresses for each level. Here you can see additional options in the software for variable amplitude loading, sometimes referred to as mission loading or duty cycle loading, as well as gradient files. If a specimen or a component does have a stress profile, like surface roughness due to the AM process, as Animesh described earlier, or an induced residual stress due to surface enhancement, like shot peening, those can be accounted for here. And the final step of the Design Explorer are additional features like defects. the probabilistic population of these microstructural defects, the voids, the pores, inclusions, the non-melt areas, as Bob described. For our forged example, we have none of these. Also, there are asperity factors available, which model the tortuosity of the fatigue cracks as they propagate. Other features in the software include the options for computationally modeling the individual fatigue stages, the crack nucleation, small crack growth, and long crack growth, as well as custom geometry factors or beta factors in the fracture mechanics simulations that VPS-MICRO performs. So having put all of our inputs in the model for our example, this forged beta Ti-64 material, as well as the geometrical parameters of the fatigue specimen itself, we come to the simulation setup page. And this provides a summary of all of the main inputs for the model and lets you know if there's something missing before you commence running the simulations. And as I said at the outset, we'll be simulating 100 simulations at each of our 6 load levels for a total of 600 simulations. After the run's complete, you would see a simulated SN curve for all 600 specimens. And if you look at the higher stress region and you can click into any one of the outputs, you can see I can hover over the output and click into that, and I can see the individual simulation for that stress level. It's number 70 out of 100, and it provides all of the critical information for that simulation, including the fatigue life and the components of fatigue life that make that simulation, how much time was spent in the nucleation stage, if there was short crack stage, or if it transitioned directly to a long crack stage, and information like that. I can also, for any one of these simulations, in the results section at the bottom of the software, I can click into the life prediction histogram of all 100 specimens of the simulation, and you can see a histogram of the breakdown of the total life, the short crack life, if there were the long crack life. And so you can computationally look at the results of each of these these outputs in the software. I can also look at the failure parameters in a computational way, breaking up into the statistical histogram. All of these types of analysis of this output data can be used in a verification validation sense with test data you might have, so that your model can most accurately describe the conditions that you're seeing in a real world physical sense. And there's also a detailed results view, which basically is a large table of all of the outputs for that group of simulations at that load set. And you can export them to Excel for further post-processing if needed. So I'm going to go back to our simulated SN curve that you see here for all 6 of our load levels, and transition back to this information. This is the same simulation information that we saw in the software, but I'm also plotting it against some forged specimen physical test data that we have. And the numbers that you see on the right-hand side of each of these load sets denote how many of the 100 simulation at each stress level were runouts or test suspensions. So we've looked at simulating the forged condition for this alloy here in VPS-MICRO. But what would be different, microstructurally speaking, about the EBM condition, and how would that change some of our model inputs? So looking at those microstructurally and looking at the differences, these 5 modeling parameters here, grain size, parameter frictional strength, specific fracture energy, defect size or presence of defects at all, and asperity factors. These 5 parameters were identified as being different between the forged condition, which you see in this column here, and the EBM condition, which you see represented by the vertical build and the horizontal build in these columns here. And the values in red from the EBM samples are measured values. So those are things that have been measured by researchers, and so we've accordingly taken those measurements and updated our simulation model with these values. And here you see the updated simulation results here for the horizontal EBM condition compared with some published fatigue test data here in orange for the horizontal build EBM Ti-64. And as a reminder, the image of the horizontal EBM microstructure that we previously showed is here again in the bottom left. And we'll also show updated simulation results for the vertical EBM condition, compared again with published fatigue test data for the vertical build EBM. And the image of the vertical EBM microstructure again is provided here. And so the model in both of these cases is showing good agreement with the limited physical testing data there is. And now, using this method, we're able to gain confidence in the scatter of the fatigue with the help of these computational models. And it's important to note that this can be scaled up from the specimen level, as we're looking at here, to the component level, where, as you might recall from the certification testing pyramid, to which Animesh referred at the beginning of our presentation, the necessary resources for those component level tests can be orders of magnitude larger in terms of time and cost. So we also wanted to touch on some of the other things that we've been doing in AEM. Here you see some collaborative work that we've done with A-STAR, which is an advanced manufacturing consortium in Singapore, on selective laser melted IN 718. The volume element that's on the upper right-hand side of the image here is showing how the microstructure varies in different directions due to the SLM process. Specifically here showing the grain size and orientation. And these probabilistic values are direct inputs for the VPS-MICRO ICME type of modeling. And not only in matters of fatigue, we've successfully modeled other mechanisms in the failure spectrum, such as burst failure or overload fracture. Here with Aerojet Rocketdyne, we predicted the burst failure location and pressure magnitude for various AM process settings in Mondeloy. These settings produce different levels of quality in the material, vis-a-vis how many pores and voids were present and their respective sizes. And so that depending on the speed and feed of that AM process. And with Eaton Vehicle Group, we studied surface treatment effects on fatigue. Now, this wasn't specifically additive, but it does show a good example of how surface condition of the same alloy can have an impact on fatigue performance. So the Eaton Vehicle Group built gears for single tooth bend fatigue, but surface treated them differently. And we were able to characterize and model those. And if those can be characterized sufficiently, the software can model the impacts that those differences in surface treatment have on prediction of fatigue. So I'll wrap up here by saying that we can work with clients in a multitude of ways. We offer the software shown here as a license subscription with support, though sometimes that level of support might be greater than, say, normal. We also offer consulting agreements if that makes sense to go that route as well. That really concludes our presentation. Animesh, Bob, and I thank you for your time and your attention. Welcome any questions you might have. Jason, I'll turn it back over to you.
All right, thank you. Excuse me, thank you very much. Let's see. So we'll now head into the Q&A session. If you do have questions for our presenters and you haven't done so already, please type them into the question box. I do have a couple of questions here to start with. Let's see. So, hold on one moment. Let me pull these up. Okay, so first question. Is it possible that a lower level of agreement test versus simulation at 50 KSI on the SNN curve has to do with some changes in crack initiation mechanism?
That's a good question. I think, Bob, would you have some input on that between crack initiation or nucleation, depending on the mechanism?
Yeah, and Mike, can you go back to the SN curve, because that's definitely true. Yes, is that as we drop in stress there, and this is a good example. But you do notice that there were, in this particular case, as you get towards 50 KSI, in this case, you've got 71 runouts. So you still have a large percentage that run out, but you might notice that there were also some failures that say 1 times 10 to the 5th, and whereas the part or the one part that was tested failed at say 2 times 10 to the 6th. So indeed, even in the model, mechanistically, what's going on at 70 KSI will be different than what's going on at 50 KSI, and capturing that mechanism, especially by looking at the fracture surfaces. And noting from the fracture surfaces, we have to do some testing and see did that mechanism switch over. And in this case it wasn't, but you can start to get internal cracking, especially at the very low stresses. And these are mechanistic models, so you have to explicitly put that mechanism in. Now you can put it in and run it, and if it doesn't fail, well, that's fine. But you do have to understand mechanistically what's going on, and changes in the mechanism, especially internal versus external, transgranular versus voids, and at what stresses those happen. The model should be able to capture that, but you still have to make sure that you've got them as one of the allowable failure mechanisms.
All right, thank you very much. So let's see, next question. All right. Let's see, it says, how are the microstructural features generated, such as the distribution of grain size, voids, and inclusions?
I think I'll take that one. So those distributions within VPS-MICRO are generated in a Monte Carlo type of sampling sense. So the inputs are gathered through some limited physical observation, as we said, metallography, particularly for the grain size and defect information. So that is gathered in a metallographic sense to determine what those input distributions are. And then as the software populates these stress volumes with the microstructure, the software will pull from those input distributions of the grain size and population density and size of defects and create these virtual microstructures in a Monte Carlo type of sampling sense.
All right, thank you. Another question. I wonder whether VPS-MICRO could allow us to get the convergence in the macro model. For example, we increase the number of FEs and the number of RVE on each FE would be also increased. The computational runtime would be expensive. I'm not sure if he's asking if the computation would be expensive or.
Right. That is a good question. Yeah, go ahead, Bob.
I can kind of answer that. So what we have done is we run the entire component. So that's why, as Mike showed in there, the area of a SN curve. So the area of the component. So if you have a component with 1 cubic inch versus a component with, say, 10 cubic inches, we're going to run that entire component because we find that fatigue indeed is driven by the size of the component. Now, there's some convergence after you get above a certain size, but most fatigue specimens are fairly small, so they really haven't converged yet. So you could use micro to find out at what size would your fatigue strength level off, but oftentimes that has not been met with a component. It may have been met with, like, a wing spar or a spar or something. So that's a very good question there, and that's why we modeled the entire volume of the actual components we're simulating.
If I could add just one point here, perhaps to elaborate. We are not running the RVE model along with the macro FE model. Those are separate. So the RVE model is run separately, and then the uncertainty information from that is then put into the global, or the part model. So that helps quite a bit, or that does not bog down the runtime.
All right, thank you. So let's see. When starting a new material, how much time, cost, and effort does it take to obtain the data to support VPS-MICRO?
I think I can take that question. We very recently had a program with one of the airframers. Well, actually, the Air Force provided us with a chunk of materials. They took a billet and they cut a square. They cut a chunk of it off. And then we sent it out to the independent laboratory. So Vextec did none of this. We sent it out those, and we told them what to do. So we came up with a test plan. They machined the specimens, they tested the specimens, and they provided everything back to us. And this was for the beta and the Ti-6.4 actually that Mike showed in the example. And that was a little under $15,000. So it was, and it probably took, I'm going to say 6 weeks for them to machine stuff. So that's what it kind of took for us to gather the baseline material model. Now, I'm not going to say that that gathers enough material model to fully calibrate the model, because a full calibration to a -3 sigma takes a very large amount of data, and we've done that with people that own that type of data. But to get a good model, model that's started, takes about a 15K worth of. These are all typical ASTM tests, so there was no special test.
All right, thanks. All right, I think we have one more here. Oh no, we got a couple more in here actually. Well, I wasn't looking. All right, so let's see. On slide 21, why were there multiple simulation outputs for the same stress condition? Was the input data different for each stress condition?
Okay, so I'm on slide 21. The outputs from the simulation are represented by the open red circles, and the test data, the physical test data, by the closed blue circles. Now, the reason there are multiple outputs for the red circles in the simulation is that describes the type of scatter in the fatigue test, in the fatigue response of a material. So if you were to physically test 100 specimens, you may expect a range in fatigue life that you would see in the computational output. So there are differences in the input side due to these probabilistic inputs. So each time a simulation, a realization of a test specimen, for this example, every time a test specimen is realized in the software, it has a different set of microstructural inputs due to these probabilistic distributions that are used. So but all of them are statistically within the same family that you would expect to see in a physical specimen. But if you were to have all of these specimens machined to the best tolerances you could and have the same geometry, the same loading condition, you would still see varied outputs due to the natural variation in the microstructure. And that is what this simulation is capturing in this case.
All right. Excuse me. All right, so next question. When FEA stress is used, is there a way to align the orientation of the stress tensor to the build direction?
And I can comment on that. Now, when you're doing the FEA model, which is, we just use standard ANSYS, Abacus, and Nastran. Well, then you can take your, if you know what your stiffness matrix is, you can orient that stiffness matrix according to your stress tensor using those traditional methods. Now, in VPS-MICRO, we absolutely do. That's a very important thing, and that we've got a parameter in there called the orientation. So you put in the texture. So if you were to do, say, a EBSD and find that there is a texture, and that texture has a relationship to the build direction, you put that into the software. So there's a specific file that you pull in when you can put your texture, and you can relate your texture to the loading direction in when we're doing the fatigue modeling itself. Yes.
Okay, let's see. Can the user specify the confidence level of the resulting fatigue data?
Animesh, do you want to comment on this one?
Not directly. So VPS-MICRO results do not kind of readily output the confidence level, but I think if you recalled, the results could be exported into Excel, and all the simulation results are tabulated, and one can compute the simulation or the confidence bounds on each of the predicted results as well as the failure parameters. Additionally, I think we also allow a restart feature in the software. So let's say you ran 100 simulations and then you kind of computed the confidence level. If it's not falling within your prescribed range, you can add more simulations successively without losing prior data till you achieve your desired confidence level.
Okay, thank you. Let's see, we've got a couple more here. Is it possible to consider the fatigue analysis simulation at very high temperatures, for example, 700 degrees Celsius?
I guess I'll take that. If you know what the mechanism is because you may well get a mechanistic change going on. So your material, but you'd have to go in and put in your material properties for 700C. And if there's a mechanistic change, put it in. Now, if you've got something like a dwell, cyclic dwell going on, then micro by itself will not allow you to put in cyclic dwell. However, if you have a lot of softening going on, you can put the softening in. So you have cyclic softening. So it will capture 700 degrees C, but you have to explicitly capture data at 700 degrees C, and it will not capture dwell effects.
All right, thank you. Let's see. Can you also generate an EN curve?
Yes, and we generate an EN curve by knowing what the cyclic stress strain curve is. So in reality, micro runs at the strain. So the interior equations from micro are all strain based. We convert them back to stress based because traditionally we worked in companies that did a lot of stress based stuff. But yeah, so we generate the EN curve, but we do need to have some good idea of what the cyclic softening or cyclic hardening is. So that has to kind of be done experimentally. We will not be able to predict to predict explicitly cyclic hardening or softening.
All right, thank you. All right, and here's our last question. That was a very, very good Q&A session we had there. One of the most challenging predictions in LCF behavior is fatigue scatter. How can the accurate predictions of LCF scatter be assured with relatively low amounts of test data points?
And I think I can comment on that. That is how we have done it, is actually go back over the years and gathered empirical data where people have done large amounts of testing and looked at that and kind of compared that to our models. It's very difficult to accurately, as you say, predict the very low life, especially if some other damage mechanism comes in there. But the beauty of these models is that you can model them and then go at each of your low life specimen and look to see what drove that low life specimen. Was it a large grain? So you can kind of make an engineering judgment on whether that makes sense. Now, if you think about it in the issue of if I'm going to do a fatigue test of many specimens and I've got ends up with a large volume, say, 20 cubic yards of material, you could have a defect in there that you did not realize and have in your model. So really the challenge here is making sure, capturing that there is a mechanism in a very large volume of material that you didn't miss. Now, one way of doing that, we worked with the Air Force with that, is put mechanisms in there. Mechanisms we did not observe, say, defects in a titanium, a hard alpha in a millennial titanium. We didn't observe it, but if we put it in the model and we let it occur, say, for once for every cubic yard, how does that affect risk? But we can only use really engineering judgment to make sure we've captured the mechanisms that are going to accurately predict those low life specimens.
All right, great. All right, great Q&A session. Thank you everyone for your questions. All right, so I guess that'll wrap up today's TRX webinar series. I would like to once again thank our presenters, Mike, Animesh, and Bob. If you do have further questions for any of our presenters, you can reach out to them directly at Michael Oya's email address, which is on our screen now. It's moja@vextec.com. And this will be posted to the America Makes YouTube page. So if you want to go, if you don't get it now and you want to revisit this presentation and get that contact information, it will be posted there within the next couple of days. There will also be a post-webinar survey going out to all of those who participated. We do really appreciate the time that you take to provide America Makes feedback so that we may continue to improve and strengthen the additive community. And as a reminder, if you think that you or your organization will be interested in sharing on the TRX webinar series, you can fill out the form that follows the presentation, or you can reach out to myself, Jason Thomas, directly at jason.thomas@ncdmm.org. Thank you very much and have a great day.
Thank you all.